Hello, everyone. We're working through Chapter 13, Part 1 in an Introduction to Statistical Methods and Data Analysis by Ott and Longnecker. In this chapter, we're going to be talking about model building and diagnostics. So one thing when you build your regression model that you're going to want to check for is that your independent variables you don't want them to be severely correlated with one another. So we're going to assess the collinearity. And by doing this, we're going to first look at a correlation matrix, and we're going to see if any of the correlations are above somewhere around 0.9, because this would tell us that we're having serious problems with collinearity. So right here, we see college and age have a very strong relationship with one another. Crime and income, we see have a stronger correlation, but not too high. And we continue to look at these. So one thing that we might note is we may not want to build a model that has both college and age in the model because they're too related. So when we look at our scatter plot between college and age right here, we can see that there's that strong linear pattern. Another thing that's really nice about looking at the scatter plot matrix in general is you could see if you're going to need any transformations of your variables. So for example, age and crime, right? We have this parabola kind of shape. Here we might have some groupings, right? Between age and crime, there might be two different relationships. So getting the scatter plot matrix can really help us understand these relationships. But overall, college and age, we would highly consider whether or not we're going to include both of those variables because of the high correlation. The other thing we can do is we can calculate the variance inflation factor. So for every variable, we can essentially regress that variable on the rest to see what that R squared value of regressing xj on the rest of the explanatory variables. If our variance inflation factor is greater than 10, that's going to indicate collinearity issues, and we should consider refining our model further. So let's do an example. Okay, so we're going to fit a model. And in this case, we have crime is our Y value. So we have crime. And that's going to follow age plus college plus income plus sex. All right, so when we fit the model, this is our Y follows X1 plus X2 plus X3 plus X4, right, for our linear model. And then essentially we're going to get those coefficients. But after fitting this model, we're asking ourselves, what's the relationship between our X variables? So what's the relationship between age, college, income, and sex? So what we do is we're going to fit 4 different models so that we can get each of the R squared J's. So here I first fit age on college, income, and sex. And then I'm fitting college on age, income, and sex, income on age, college, and sex, and then sex on age, college, and income. So essentially here, fit 1 is giving the regression model for age as the xj as the response variable or the dependent variable on the rest of the variables. So what I can do is I can pick off the R squared value from each of those models, right? So essentially here, by using summary of fit.1 $R.squared, that's going to give you the R squared value of age regressed on college income and sex. And then if you do summary of fit 2 $r², that's giving you the r² J value for college regressed on age, income, and sex, and so on. So to calculate the VIF, you just use the formula 1/1 minus r² J, and then we can check all of these values. So the rule of thumb is greater than 10. So the VIF for age is 6.8, for college is 7.5, for income is 1.7, and for sex is 1.25. So overall, none of them meet that 10 threshold, but we do see that college is getting up, like the variance inflation factor is getting bigger and bigger. Okay, so essentially, to avoid collinearity, one thing you want to do is you want to choose your variables very carefully from the beginning of your study so that each of those variables reflects a different component of the response variable. Okay, it's okay for your independent variables to be related, but you don't want that relationship to be overly obvious. Otherwise, you're going to have issues with your model where you think you know more than you do, right? So how do we choose this best model? It's always a balance where you don't want too many variables, but you don't want too few variables. So what we can do is we can use some criteria to decide which model is best. The first criteria we're going to talk about is the r² criteria. Okay, so in every model, we can pull off an r² value. And remember that r² ranges between 0 and 1, or 0 to 100%, right? And essentially, as you add more predictors into your model, then your r² value is going to increase. Because if you have more information, your model should be doing better at making predictions. So what I'm going to do here is I'm going to fit 4 different models. And what we've done is we've fit crime just on college, and then crime on college and income for fit 2. And for fit 3, crime is regressed on college, income, and sex. And on fit 4, crime is regressed on college, income, sex, and age. And what I'm going to do is I'm going to calculate the r² value by pulling off the summary of your fit $r². Okay, by doing this, we get the 4 r² values from each of our 4 fitted models. And we see that, as we said before, as the number of variables in your model increases, this r² value is also going to increase. So based on just the value of r² alone, I would say that you would end up choosing fit 4. Fit.4 has the highest r². But I'm going to note that fit.3 has a decent r² value. And from before, we knew that the correlation between college and age was somewhat high. So fit.3 might be the model that you end up choosing. Fit.3 has a decent r² value and could also be used. All right, the next criteria we're going to talk about is the adjusted r² criteria. So in the r² situation, that r² value is going to increase no matter how many predictors you put in the model. But we might have an issue with overfitting. If we put more and more variables in the model, are we really making a better model, or do we just have more and more variables? So essentially what you can do is you can penalize the R squared value based on the number of predictors in your model. And what you do by doing this is that you're going to take your SSE and divide it by the degrees of freedom, and take the SST, divide by the total degrees of freedom. And essentially, whichever formula you use, you can get that R squared adjusted value if you want to calculate this by hand. Another way to do this is just to fit the models as we did before. So we can have fit 1 through fit 4. And to pull off the R squared adjusted, you're just going to do summary of your fit. So for example, summary of fit 1, $ adjusted .r squared. And that will allow you to pick off the adjusted R squared value. Now, in this case, now that R squared, original R squared, is being penalized by the number of predictors in your model. So the R squared adjusted values are slightly different than the R squared values. And when I look at this, we would still probably choose model 4. Right? Fit.4 would be what we would choose. Has the highest R squared adjusted value. But we noticed that the difference between model 2, model 3, and model 4, they're not that far apart. They all do particularly well. But overall, we're probably going to choose that model 4 or even maybe the model 3, right? It's kind of, if you're just going based on the numbers, you would choose model 4. If you're looking at how well of a fit and the fact that age and college are somewhat collinear because of the correlation between the two, then maybe you'd choose fit 3. All right. So overall, one thing to note is I only fit 4 models here, but really you could think of lots of different models, right? Because essentially crime could be regressed on college, right? Crime could be regressed on income. Crime could be regressed on sex, and crime could be regressed on age. There's 4 models with just 1 variable. And then if you think about it, there's really 4 choose 2 models that have 2 predictors in the model, right? And then there's 4 choose 3 models, which is equal to 4, that have 3 predictors in the model. And then there's 4 choose 4, which is just 1 model that has 4 predictors in the model. All right. So essentially, I might not want to have to think about all these different regression ways to do this. So instead, I can use a package called Leaps. And what you're going to do the first time you use R, and I'll pull up R in a bit, maybe in the next video, is you're going to have to install a package. So you're going to do install.packages, and then put in quotes, Leaps, and then comma, dependencies equals true. And when you do this, for the first time that you ever install the package on your computer, you'll have to use this install.packages command. Once you've ran this on your computer one time, you don't need to run it again. You will just get to start with this line of code that says library Leaps. All right. So in order to do this, we can take our data set And we can split it up by X and Y. So in my particular data set, if you look at it, you had crime as the first column. And then we had college, income, sex, and age. So what I want to do is I want to break this data set up into two pieces, where this is the Y value and all of these are the X values. Okay, so what I'm doing is I'm saying let X equal my data set from the second to the fifth column, and let Y equal the data set, comma, just the first column. So that's these two pieces here. So I'm trying to separate out the X and the Y, right? And the LEAPS package, what it's going to do is I'm going to have it calculate all the different models that we just talked about of size 1 through 4. And I asked it to calculate the R-squared criterion. And when I do this, essentially here, I'm saving the output of this LEAPS function to an object called criterion. And then I'm picking off the size, the R-squared value, and which variables were selected. So here I can see the value of R-squared for different size models. Okay, so let's walk through the first line. Essentially, when I regress crime on income only, so there's one variable in the model, which means that there's two predictors because I have a slope and an intercept, right? So I have income and the y-intercept. The R-squared value is 0.6645. And then age is not in the model. College is not in the model. Income is in the model. Sex is not in the model, okay? And this essentially fit all of the models of size 1, right? Then it fit all of the models with 2 variables in the model, and then all of the models with 3 variables in the model, and then the model with all the variables in the model. And if I look at this list very carefully, I can see that I have a few different choices that have pretty high R-squared values, okay? Essentially, if I look at this fit, the model with age, income, and sex to predict crime has an R-squared value of 0.8364. And the model with college, income, and sex has an R-squared value of 0.8133, right? And then I have the model that's 0.8365, which has age, college, income, and sex. Okay, so when I look at these 3 choices, I'd probably end up choosing this model as my final model because the R-squared value is 0.8365, but I have less predictors in my model, and I know that age and college have somewhat of a high correlation. So at the end of the day, I would end up choosing my final model to be crime regressed on age plus income plus sex. All right. So this is just getting you started with model fitting. And in our next video, we're going to go through another example of the LEAPS package.